Good afternoon, everyone.
Hello, sir.
I hope I can be heard. Thank you very much. So today we will look at camera calibration first. That means obtaining the parameters of the camera without knowing them by just using images taken from the camera. Later on, we will be able to use this knowledge to obtain finally the measurements of objects that the cameras can see. And then finally, when we think about more than one camera, multiple cameras, we can use this knowledge to obtain a 3D reconstruction. So this is the multiple geometry pathway that we have to study in this course. And in the latter part of today's class, we will start looking at convolutional neural networks. The reason is that also needs a little bit of time to comprehend. So we will start that and slowly get used to coding a little bit using the important package called PyTorch. Okay. So we will go through this lesson quickly. So we have to see why we require this. Then we will look at the so-called perspective projection model. Intrinsic camera parameters, that means the camera parameters that are internal to the camera. Then extrinsic camera parameters, the camera parameters outside of the camera that gives you the pose of the camera, where the camera is looking at. That means the 3D coordinates of the camera center and its orientation. Then we will look at calibration, that means how to obtain those parameters. And then finally, we will look at triangulation. That means when multiple cameras are there, how to find the 3D location of a point up to some certain ambiguity. So the general question that we ask is, given an image, can we recover the 3D structure? Under certain conditions, using one camera you can, but usually you need more than one camera. Because as human beings also, we have been given two eyes. You know that those two eyes are there because we want to see in 3D. We want so-called stereo vision. Depth estimation is there because we have two eyes. So people can do different kinds of tricks uh, with cameras. You can see this pumpkin image has been obtained by setting the camera's aperture to a very small value and keeping the camera near the pumpkin, and both of these people also being in focus. This also has been done like that. The camera is close to the person, tower of Pisa is there in the background, and the camera has been adjusted to have a very small aperture. Okay, so let's look at this so-called single view ambiguity. Now, think about this as the camera. This is the camera. And we have the image plane here. This is the image. And we have a point that has been imaged. Now, as you know, the cameras, when they look at an object, now this is the camera. So this is, you can see this is the lens. This is the CCD or the film of the camera. So there is some object here, maybe a tree or something. So an image is formed right here. An image is formed right here. You can consider it upside down. An image is formed like that. As these triangles can have the similar triangle theory applied, rather than locating the film or the CCD behind the camera lens, we can also equivalently locate it in front of the camera, as you can see here. So these are equivalent. You will get the same image size, even if you locate it here. So therefore, you can see that's why the film or the CCD or the image plane has been located in front of the camera. Now, that is not what we want to study here. What we are studying here is, given the small x, this is an image of a point. So we use small letters to designate images, image of a point. Where is the actual 3D point? Where is the actual 3D point? You will realize that because these rays go to the camera center go through the camera center to strike the film like here. So therefore, this object can be anywhere along the ray, because you can see it is a straight line. Anywhere along that straight line that joins this image point and the camera center. This is the camera center. This is the camera center right here. This is the camera center. That's the camera center. It can be located here, there, or anywhere along that ray. This is the ambiguity. So if we have an image point, we do not exactly know where the 3D point is. In other words, we do not know the depth of that point. So that is why you can do crazy artworks like that. You can see this one is in 3D, but when you cast light, you can get a beautiful 3D picture, this kind of thing. And then people can draw these things on the ground and show crazy things, right? And here this is called anamorphic perspective. These artists used to do this. And what does this contain? This picture. So if you sort of distort the image so that you are looking this way using a camera or something, you can see it is a skull. This is to show the that death is on us, right? I mean, it's a reality. So our goal is to recover the 3D structure. When certain assumptions hold, we can recover a structure from a single view. In general, we need multiple views to recover the 3D structure. But first, we need to understand the geometry of a single camera to be able to do this. Okay, that's a motivation. So let's look at the perspective projection model and then intrinsic camera parameters and extrinsic parameters. Okay, so this is the perspective projection model. As I mentioned before, the camera center is here and the image plane is in front of the camera. Actually, image plane is behind the camera, but equivalently, we can represent it like that. So here is a 3D point in the world that we note as capital X, and that has been imaged at the small x, because we can cast a ray from this capital X going through the camera center, as you can see. So when this ray cuts the image plane, that's where capital X's image, small x will appear. Now, camera's y-axis is this, camera's x-axis is this, camera's z-axis or the principal axis or the optical axis is this. And this one is the x-axis in the image, this one is the y-axis in the image. I hope that this geometry is clear to you. Any questions about this geometry? Are we okay? Okay then. Now, normalized camera coordinate system, the camera center is at the origin, the principal axis is z-axis, x and y-axis of the image plane are parallel to the x and y-axis of the world. So you can see this y-axis is parallel to the image's y-axis. This x-axis of the world is parallel to the image's x-axis. Now, we can get a 2D picture of this by looking at this scene from this angle, right? If you look at this scene from this angle, yeah, we can get this picture. Now, this distance is called the focal length. F is the focal length. And this is the camera center. This is the optical axis, z-axis, as you can see. Now, if you look from that, this height is y. You can see that this height is y. And this is the world point. We write this as capital X is actually X, Y, and Z. Actually, you usually put a 1 also at the bottom that we can do later. Okay, and this is the image point. It has X, Y coordinates. We are only considering the Y coordinate now. I hope the geometry is clear for you. This Y is height, right? And this is Z, right? I hope that this is clear. Okay, now using this triangle and using the larger triangle, which is this one, this triangle, by applying the similar triangle rules, we can obtain an expression for the small y. This is what we are going to do now. Okay, so this is my small y. Okay, you can see that small y, this one, divided by f of this red triangle is equal to the capital Y of the blue triangle, that is this y, divided by this distance, which is capital Z. Yeah. From this, you can get this expression y is equal to f y over z. It's very easy. So this is what I have written here. You can obtain a similar relationship for small x also. So now you can see we have been able to represent the image coordinates of that point, capital X, capital Y, Z, in terms of capital X, capital Y, and Z, and the focal length of the camera f. Now we want to write this in a matrix form because we always manipulate matrices. In matrix form, it is like this. So you can see it is exactly the those equations that I have written. So this has these, as you can see, it's a 3 rows by 4 columns matrix P. Yeah, and this X, as you can see, is a 4 rows and 1 column matrix, and the resulting answer is actually a 3 rows by a 1 column matrix or a vector. And as you know, this F multiplies with this Y, X, right? And this 0 gets multiplied with this Y, and this 0 gets multiplied with this Z, this 0 gets multiplied with this 1. So therefore, what you get is Fx from that. All others are 0. From the second row, you have an F here, and all others are 0. That F will multiply this Y. So therefore, you can see in the second row, you get Fy. Third row, there's only one here. That one multiplies this Z, you get Z. Okay. Now, we know that this is the X coordinate, somewhat related to that. This is the Y coordinate, somewhat related to that. So X coordinate, to obtain the X coordinate, you must divide by the last number, because we know that this is what we want to obtain. Here also, this is what we want to obtain. So from this vector, if we divide by the last number, that means Fx divided by the last number, divided by Z, Fy divided by the last number, which is Z, and if we divide Z by Z1. So this is what we have, and you can see there we have the X coordinate in Cartesian form, Y coordinate in Cartesian form, and 1 there. So this is the most simple perspective projection model. So this is how I have done that. I have divided that, as you can see. So there is an unknown scale factor, lambda. So therefore, the image in geometry, this is a very important equation. We write it as lambda x equals px. P is a camera matrix. X is the 3D coordinates of the world. X, Y, Z, and 1. And small x is x, y, 1. And the unknown scale factor lambda is there. So therefore, we write equality up to a scale with 3 lines in this computer vision geometry. X equals px. Okay, let's move forward. Now we have to consider the world coordinate system, because now usually the camera is located somewhere in the world, in a room or something. We may have located the coordinates of the measurements of that we have done on the room in some coordinate frame, maybe with respect to the corner of the room. So there is a rotation matrix and translation matrix between the camera and the room. So you can see that the camera is in the room, so there's a rotation and translation matrix between the camera and the room. So therefore, in camera calibration, we have to incorporate those, figuring out transformation from the world coordinate system to the image coordinate system. So finally, what we will get is this. We have the X, that is the 3D vector, the world coordinates of capital X, and then we will have the rotation matrix, uh, world to camera coordinate transformation matrix, RT0 and 1. So this is a 4 by 4 matrix. R is a 3 by 3 matrix. T is a 3 by 1 matrix. We will look at that in more detail later. And this one is called the canonical camera projection matrix. It's a 3 by 4 matrix. It has I3. I3 means a 3 by 3 identity matrix and a column of zeros. These are row of zeros. And then we have the camera pixel coordinate transformation matrix, or the intrinsic camera calibration matrix K, which is a 3 by 3 matrix. And then we get the 2D point on the image, a 3 by 1 matrix, which is lambda. Okay, now let's go into details of this. This is called the extrinsic camera parameters, rotation and translation. Extrinsic means outside the camera. It depends on where we keep the camera. And intrinsic camera parameters, pixel point, scaling factors, principal point and scaling factors are there. We will see the details later. And this whole thing we call P equals KRT. KRT. So you will see the details later. Okay. Let's first of all incorporate the principal point. Principal point is where principal axis intersect the camera plane. So you can see this is the principal axis or the optical axis or the central camera's central ray. So it is perpendicular to the lens array. So if you think that this is the camera, so this is where the CCD or the film is. This is my lens barrel. Okay, this line is my capital Z line. Goes to the center of the lens. Okay, principal point is where the principal axis intersects the image. So you can see now this principal axis intersects the image at small p. This small c will have y-cam and x-cam coordinates, but what we want to do is to measure these coordinates not from the center. Like if you take an image, you don't measure coordinates from the center, right? You measure from based on a corner. Actually, in our course, we measure from this top left corner. So that has to be incorporated. Yes. So in the normalized coordinate system, the origin of the image is at the principal point. In the image coordinate system, the original is in a corner, in the corner. So let's do that transformation. We want the principal point to map to px/py instead of 0, 0. Okay, so therefore, in the equation that we had earlier, fx divided by z, we had to add px. Yeah, then the trick is done. Y equals f divided by f times y divided by z. We had to add py. Then it's done. So now we can have to incorporate that into the matrix form. So therefore, x, y, 1 lambda, we saw that before, fx plus z px. And of course, this z is here. When you divide by z only, you get this, as we saw last few minutes ago. Then you can see the matrix is like that. F0 px, yeah, this px multiplies z. And then this py also multiplies z. So now you can see it is taken care of. So into the matrix, we incorporated the principal point coordinates, Px and Py. Actually, these principal point coordinates, if your CCD is, let's, I don't know exactly the size. Right now, I don't remember. Maybe it's, let's say, for the time being, I think it's slightly less than that, 40 millimeters and 30 millimeters. Let's say this is the size. So the center is like that. So therefore, the coordinates here, if the origin is here, coordinates here will be how much? First coordinate is vertical coordinate. Yeah, first coordinate is the horizontal coordinate in this formulation. That's not the correct case though. 20 millimeters, comma, 15 millimeters, right? Half of those, 20 and 15. That's what px is. This is my px, and this is my py. I hope that's clear to you. So now we have incorporated that. Remember, all these things are in millimeters. These is millimeters, 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 millimeters. Okay, I hope that point is clear. Principal point has been incorporated. Now, if we write it in that form, we can have a 3 by 3 matrix, and this one which is equivalent to this. You can check. I will show you for one number. So take f multiplies 1, this 0 multiplies this 0 and this 0. So therefore, you get f here. So do the multiplication and see. You take the row and multiply this column. You get this number. Multiply this column. Yeah. To get this number, it's 0. You take this column to get this number, and finally multiply this column with that row to get this number. Okay, I hope this is clear to you. So if you have any question, please don't hesitate to ask as usual. Yeah. So now you can see this is called the camera calibration matrix, canonical projection matrix, and P equals KI 0. Yes. Okay. Again, what are the units of the focal length? If in principal point coordinates and principal point coordinates, if they are in millimeters, same as world units, presumably metric units. What units do we want the measurements of image coordinates be? But image coordinates we want in pixels. We don't want them in millimeters. So we measure them in pixels. So pixel units. So thus we need to introduce scaling factors for mapping from world to pixel units. Right. That is based on the camera sensor. So this is a picture of a camera sensor. So the scaling factors are there. These scaling factors show the size of a pixel. So mx is the pixels per meter. So I like to call them pixels per millimeter in horizontal direction. My pixels per millimeter in vertical direction. And then you can see the pixel size is 1 over mx times 1 over my. Very small. Okay, let's see how we can incorporate that. Right now, the calibration matrix K is in meters or millimeters. Now you can see, if I have the scaling factor mx here, so mx pixels per meter, f is in meters. So here you can see this column as this multiplies this row as this multiplies this column, you will get mx times f. When you have mx times f is in, let's say, meters, actually it's in millimeters, mx is in pixels per meter, you can see what results, the unit that we get will be in pixels. Right? I hope you can see that. So we are incorporating the internal parameters of the camera to obtain these numbers in pixel units. All right. So then we do not have f anymore. We have alpha x, that is focal length in x direction in pixel units. Alpha y, focal length in pixel units in y direction. Beta x, principal point in x direction in pixel units. Beta y, principal point in y direction in pixel units. This is called the camera calibration matrix. I hope you can understand that. All right. In general, camera coordinate frame will be translated related to the world coordinates frame by a rotation and a translation. This is that rotation and translation. So in non-homogeneous coordinates, I'll talk about homogeneous coordinates a little bit later. The transformation from world to normalized camera coordinate frame system is given by x cam is equal to r, that's a rotation matrix, x tilde minus c tilde. So there are coordinates of the point of a point in world frame is x tilde. So this by 3D point is x tilde, and that is with respect to the world coordinate system. That is not good enough for us. What we want is this coordinate in terms of the camera coordinate system. This is the transformation we are going to do, right? You can see that. So what we have to do is we subtract the camera center. This is the coordinates of the camera center in the world coordinate frame. So this is the C tilde. With respect to the world coordinate frame, what is the camera center? We subtract that So you can see that we get the difference, and we have to multiply by the rotation matrix. So this is the 3D rotation matrix. Coordinates of point in normalized camera frame is what we get here. So last time we looked at the rotation matrix in 2D. I hope you remember cos theta minus sin theta f x sin theta. I hope you remember that rotation matrix in 2D. So these are rotation matrix in 3D. Yeah. So now with this we can write Rx plus T. T is after that rotation. So in non-homogeneous coordinates, we write this as Rxt. But if we add the 1 here, we can write this in homogeneous coordinates if we add a 1 there. So you can see this T is actually Tx translation in x direction, Ty translation in y direction, and 1. This R is a 3 by 3 matrix. So I will write that for you to see. T is Tx translation in x direction, Ty translation in y direction, Tz translation in z direction, and 1. And then this R is, it has 3 numbers. It's a 3 by 3 matrix. What I'm writing now is R. I'm just showing you in this process to show that it is a 3 by 3 matrix. Okay, this is my R, and this 0 is 0 transpose 3 zeros. 0, 0, 0. Okay, this is that matrix. We have written in it in a shorthand form. This is that matrix. So this portion is my capital R. This portion is my T vector. This portion is my 0 transpose. This one is 1. Okay. So then in homogeneous coordinates, you can write that. Just know that in homogeneous coordinates, you have added a 1. Okay. So now with this multiplication, you get x cam. That means this capital X with respect to the camera. So that's x cam. So now it's with respect to the camera. No? The transformation from normalized 3D coordinates to pixel image coordinates will be in this form. So now when 3D coordinate is specified in terms of the camera coordinate system, you can write KIO XCAM. And now you know this XCAM can be replaced by RT01X, like so. We replace that. And then finally, you have lambda x equals KRTX, T is equal to minus RT, RC. This is extremely important to remember that this is the perspective imaging geometry equation. Yeah, this one.
Sir, can I ask a question? That
Absolutely.
equation
Absolutely.
K in square brackets R pipe T. What does that R pipe T mean?
Yeah, it's actually just a notation. Pi does not have any other mathematical definition, the programmatic definition. So R is a 3 by 3 matrix, right? R is a 3 by 3 matrix. Rotation matrices in 3D are 3 by 3 matrices. Thank you for asking that question. Then we draw just a line, and then T is a 3 by 1 matrix. 3 by 1 matrix. So this is what we have here. So you can see R has 3 by 3, this has 3 by 1. So altogether it has 3 rows and 4 columns. That's what it is. So we are just showing that it's a combination of these two quantities.
Thank you, sir.
Yeah, thank you very much for that question. I should have told that. Okay, so if you think about the projection of the camera center in the world coordinates, so you can see I have written T as minus RC, and then C and 1 are those coordinates of the camera center in world coordinates. You can see we multiply this K and so on. So from R with R you multiply C, and with minus RC you multiply 1. Then you get 0 here. So camera center in the world coordinates. The camera center is the so-called null space of the projection matrix. That means when you do this PC, you get zero. So if you know about these null spaces and so on, you can think about it. Okay, so in summary, this is the camera matrix KRT. So if you write in slightly more detail, MX, you have the K like that, alpha X, alpha Y, beta X, beta Y. And then principal point coordinates are there, focal length is there, pixel magnification factors, MX and MY are there. And then skew is there, but I did not talk about it. And so then there can be other things like radial distortion and so on. Those can also be incorporated into the K, but right now we will not discuss how they are incorporated. Extrinsic parameters, rotation and translation related to the world coordinate system is there. To understand this, let's do a very small programming exercise. Let me get that open. I cannot find the file, I think I find it. Okay. Save this. Okay. So now what we want to do is we want to create a small camera matrix and obtain the image of a point. Okay, let's do this. First of all, import numpy as np, import file from py file. Please install that from py file. Import ply data high element. So we are going to use a point cloud. So I'll have to send you the point cloud. Airplane.ply. Okay, so I will send that using WhatsApp for now. So here is that file. It's a point cloud file. Cannot send it. Yeah, I sent it. The point cloud file. So please download that from WhatsApp. I will add to the your images folder too. Okay, I have added to the Moodle also. So this is that this is that airplane file, but now you can see this is a point cloud. Okay, you can see a point cloud here. It has been rendered in this thing, this mesh lab. I don't know too much about this. So it has been rendered, but it's a set of points. Huh? That's what we will be using. Okay. So there is a folder where my images are. So I have to locate from that, otherwise I'll be in trouble. Okay. I have to know that place. Okay. Okay. So we can import the point cloud PCD point cloud, PLY data read, and I had to give the path to that file, and this is that path. You can keep it in your very close by folder because I have this far away folder. This is what I am doing. So this is called airplane.ply. So whenever you do something like this, you know that we assert PCD is not none, right? Otherwise, we don't even know what whether the file has been opened or not. That's why we use this. Let's run this and see. No module name, ply file, py file, ply file. Okay, now it has been opened. If it complains, please install this package. I think you know how to do that. Now From this, we have to get the points. Points. This has nothing to do with computer vision. Okay, I'm just getting the points. NP dot concatenate. From the PCD. I have to get the vertex X, vertex Y, and vertex Z, and there is a reshaping requirement also. Dot reshape. Yeah, this is there. So it is a little bit cumbersome code, not related to the work that we are doing. But I will put this code in WhatsApp very soon. And X is 0 and transpose is not required. The points are there. So you can print the points dot shape, and we can subtract the mean of the points equals points minus np dot mean points along axis 1, and we can reshape 3 and 1. That is done. Mean points axis is 1. 4. Is correct?
So there's a spelling mistake in the points,
Yeah,
yes, sir.
points. Yeah, okay. Right. Now this is done. So we can we have the point out now.
So below that also there is a print points dot shape.
Thank you very much.
Below that, yeah, yes, sir.
This topic has no attribute.
SHAPE, reshape. The last line, sir. Last line, sir. Yeah, SHA.
But it's not the complaining here. It used to work. Let me see in the previous one.
Maybe you have to change it to an array, sir. It's since it's a list.
Yes. It's required. It's reshape 1 and minus 1. Vertex Y reshape 1 and minus 1. Let's see again. Okay, now it has been created. So you can see 3 XYZ coordinates and 1335 points are there. Before we go further, I want to visualize these points in 3D. For that, I have a code. I'll just put that in here and show. PLT is not defined. So we can see this is the point cloud. Previously you saw it nice with rendering. This is no rendering. Okay, this part is cumbersome, so I will send that over WhatsApp to you. So you have it. I send it to WhatsApp. Now I want to create the camera and view this plane in different ways. First of all, let's create 2 cameras and do this. First of all, a rotation matrix R1. R1. So that one I'm going to create the identity matrix equals np.array. np.array. You can see I'm going to create an identity matrix 1 1 1 like this. you can see what I have created there is the identity matrix. This is the identity matrix. So let me do some alignment if it's possible to align. Like my first rotation means no rotation. Then my T matrix. T matrix. Not aligned. What is going on? Knowing the prompting. T1 equals. Let's have this translation as it must be a vector, NP column vector array, NP array. I'm writing a column vector now, like this. Okay, I will put the Z axis like minus 4,000. Minus 4,000. You can see it's far away, minus 4,000. This is where the camera is, minus 4,000. Then I need K1. K1. So K1, for the time being, I will use the identity matrix. Of course, I can have the pixel coordinates and so on, but for time being, for demonstration, I will just have the identity matrix. Okay, one. Okay, right. Now I have to construct the camera matrix. So to construct the camera matrix, I have to know the formula. It is PKRT. PKRT. Okay, P camera matrix P1 is equal to K1 times. You can see that horizontal stacking R1 and T1. Horizontal stacking R1 and T1. So this is exactly this formula that we have, right? P equals KRT. That's what we have written here. So now P is also there. So let me just print P1 and show you this camera matrix. So you can see it's a 4x1 matrix. So you can see this minus 4,000 is there. Oh, oh, it gave some stupid numbers here. Oh, the rotation matrix is, oh my goodness, 1, 0, 0. It gave a wrong rotation matrix. Here's what has happened, 0, 0, 1. Okay. Now the K1 is also 1, 0, 0, 1, 0, 0. Let's see. Fortunately, I saw it. Okay, that is our camera matrix P1. So if you have P1, how do you obtain the transform point? That means the points, transfer points, let's say images due to the first camera, X1. It's very easy. Remember, my points are three rows are there. I need to add another row to those points. So therefore, I will say points because they have to be in homogeneous coordinates. Points equals points equals NP V stack can be used. V stack NP V stack points ones points shape 0. So that's the points have been there. So I so many parentheses are there. So therefore I will create these ones here in ones equals NP dot ones points shape, and then I will put it here. One, if it's correct. Now the points have been put there. We stack points and ones. Okay. Now x will be equal to. It's a very simple formula. What is the formula? P1 x equals P1 matrix multiplication points, right? So to get the Cartesian coordinates, I have to divide x2, x1 by the last row, the Cartesian coordinates. So then after that, I will show this, create a figure, and then create this scatter. scatter of x1, scatter of x coordinates and y coordinates. This is something is clearly actually. X1, x0, the scatter is there, and I will say axis equal and PAT show x dot axis equal. Finally, PAT dot show. Okay, so that's one camera creating the image one. So I want to create the second camera also. Second camera. So I need all these things for the second camera. So I'll copy this here. Okay, camera, this is camera one. This is camera two. Camera one and camera two. Here, I'm going to change the rotation matrix. I'm going to change the rotation matrix. Okay, in this rotation matrix, x-axis is along the x-axis. That part it says 1, 0, 0 is x-axis direction, right? 1 in x-axis. Y-axis is in the y-axis direction. Z-axis is Z-axis. I want to change that. I'm going to change x-axis. X-axis should be in the y-axis direction, right? Okay. And my y-axis, I'm going to change in the x-axis direction. This is rotation about z-axis. And z-axis does not change. So this rotation I change. And then all other parameters I want to keep. K also I want to keep. So that means with the second camera, it must affect this P2, and this is T2, R2, K2, K2, and K2, this R2, T2, P2. This is my second image. I can get the second image with that from the of the same point. So x2. So, and then I want to put the scatter of that also. Yeah. All right. So x2. Yeah. Hopefully it will work. So now you can see the second. Oh, the first one is not shown. But okay, only I should put x2 here, right? Two. All right. Now you can see the airplane has been rotated. Why? Because we rotate, apply the rotation metric camera, we rotate the camera. When you rotate the camera, image will look rotated. I hope that's okay. Also, what I want to do is I want to, in the K matrix, in K2, I want to put 2's here, 2. 2 here. Now let's see what happens. Now you can see it became quite small, right? Half the size. Half the size. So this rotation matrix and translation matrix, with that we can do beautiful things. But for the rotation matrix, now I will get the formula from the internet so that I can rotate in different ways. Okay, rotation about z-axis. This is what I want to do. I just want to, without complicating that, I want to get the rotation around z-axis. So rotation around, what is this rotation matrix? 3D, 3D. Rotation around eccentric axis is cos theta, sine theta. Okay, this is what cos theta minus sine theta, cos theta. Minus NP sine theta, and then NP cos theta, NP sine theta, NP sine theta, NP cos theta. This is the 3D rotation matrix about Z axis. If you want to get other axis, you have to see how to construct the matrix. Okay, that's done. So I had to define theta equals, let's say, 30, 30 degrees. So 30 degrees, right? Rotation by 30 degrees in radians. So now this is rotated by 90 degrees. So now you will see it will be rotated by about 30 degrees. See? Can you see that? All right. Now you can understand how the camera matrix is constructed. The most important line is this one. If you understand that and if you can relate that to the slides, that's enough. That learning objective has been achieved. So I will have it shown to you. The whole thing cannot be shown. So, but I think mostly everything can be shown, right? Okay. Mhm. Camera to most everything can be shown. This I sent you. Yeah, I will keep it short. Maybe if you can take a little bit of time to do this, please do it. Then you will feel happy that you see what we discussed is happening. Please don't hesitate to ask if you have any question. You can type in the chat or you can ask at any time. I hope you are doing this. This is a very valuable knowledge, although it's simple. You can just slightly make it small. Anyone who needs more time, are we okay? Okay, then. So let's move forward. So I hope you can realize that by changing this angle, you are actually affecting the rotation matrix only. You can see R2. If you say 60, it will rotate more. It rotating more, right? So you are actually rotating the camera. When you're rotating the camera, you see the image rotating. But you're rotating about the Z axis. That's the thing. So if you are rotating about some other axis, this image will change its shape and so on. Okay. I hope that this is clear. Let's get back to the slide. Okay. So now let's look at how these parameters can be obtained. So-called calibration. Now, if you take CCD.
So, sorry, can I just interrupt you here?
Absolutely.
Yeah. So rather than let's say this PLY file, if we use a BMP or JPEG, can we do the same thing, or it's
No,
not
you cannot
possible?
do. It's not possible because this PLY file
It's a 3D file.
is a 3D file. You can see
You need to have.
they do not have 3D file, no? Because the world is in 3D, right? With these
So,
points, I'm showing points in the world.
so that means what you're saying is your JPEG and BMP, they're not 3D. They can only be 2D.
Yeah, they are images.
Okay.
They
I
are
got it, sir.
images. So this 3D thing is there. From the 3D thing, we are taking an image. Then you get a 2D thing. So the
Okay, sir. I
action of
got
a
it.
camera is from 3D to 2D, right? Yeah, that's the important thing I forgot to mention. 3D to 2D action of a camera. Yeah, that's exactly what we are doing by this multiplication.
All right, sir. Thank you.
But the beauty of this little equation is now we have simulated this action of a very complicated, expensive device called camera to a simple equation, right? Simple equation containing two matrices and one vector. That's it. So that's the beauty of this theory. People understood this theory. Okay, so now if you want to take, let's say Sony cameras, if you go to Sony, these are expensive cameras are there. You can see they are very expensive pieces of cameras. This is not for people like me, but some of you can definitely afford these cameras. I think. Not, I mean, these are Alpha 9 III full frame camera without the lens, $6,800. You can see these are cameras are very expensive. Yeah. So let's take some camera and let's say take this camera and see some reasonably expensive camera. So if you can see they have shown the CCD also features. More features, specifications, general features, more. Sensor type, this is what we are worried about. You can see 35mm full frame Exmo RCMO sensor. I don't know what that RCMO sensor is. 35.9 times 23.9 millimeters of that, right? So the horizontal, the size of the sensor is 35.9 millimeters and the height is 23.9 millimeters. That's the size of the sensor. And what is the resolution of this camera thing? The video resolution it has given. So I cannot at once find the resolution, image resolution. But what I want to know is this camera, what we are looking at, Sony Alpha 9C2, the sensor. So someone should say what the sensor is. Yes, I CMOS full frame sensor. I want to know the exact number.
So there was an article, I think, right, yeah,
There's an article.
in the previous search, I think I saw an article, a third or fourth one.
Uh, Anyways, now we know the resolution 6000 by 400. Okay, that's also, let's write down 6000 pixels by 4600. Let me write down. HD CMOS sensor. CMOS sensor. I want to know sensor number. Well, Sony should say this. I mean, they don't hide these things. Maybe this is a trade secret. Likely. Not exactly saying, right? Likely. Okay. So let's search for that.
So I have a question. I saw in the camera specifications, JPEG and RAW is there, but not that PLY format. Is there a reason for that?
Okay. You cannot use a regular camera to obtain a 3D. Obtain 3D. Regular camera produces 2D.
So we are looking at 2D cameras now, so is it, or
Yeah,
3D?
all cameras are 2D cameras.
So how do you get the 3D image then? You need a
Then
video
they,
camera,
they
is it? Or
no, they have specialized cameras for 3D. Yeah. Anyway, you can see that these kind of sensors, Sony produces these sensors. Mm, and these are sensors of image sensors of consumer cameras. I think everyone uses Sony sensors, image sensors for consumer cameras. Product lineup. Oh, now you can see these sensors, right? Um, we saw that it's a 35 millimeter, 35.9 millimeter sensor. So it must be an expensive sensor. All these are 35 millimeter sensors. So we don't know exactly which one this camera uses. Medium format. So you can see. So I mean, someone must spend some time to find out exactly what sensor it has. So they have size. So 1 or 2.3 inches, 1 inch. These 1 inch sensors are expensive. They are large. The larger the sensor, they are expensive. These are the 35 millimeter. So we saw that this resolution of the camera is 33 megapixels, right? 6000 by 4000. Maybe slightly an old camera. Let's look at this one maybe. Product information IMX455A. I don't know these things, okay? So diagonal is 43.3. So I think probably it's 35.9 times sensor size. Image size, that's diagonal. So you can see total number of pixels is much more huge than this thing we used. Okay, chip size is 40.9 millimeters times 31.9 millimeters. Can I see that? Then, because we know the number of pixels, you can get the unit cell size, pixel size horizontally and vertically. I hope you can understand what we are saying here. Okay, so to comprehend that, let's do a small question. Object size question. Let me type the question and we can then answer. Consider a camera with a CMOS sensor of size 35.9 millimeters by 23.9 millimeters. The resolution is 6000 pixels by 6000 pixels. Assume that the focal length is right now, let's say its focal length is okay, that depends on the lenses.
So I have a question. Is that ratio of the width and the height related to the aspect ratio of the
Exactly,
picture?
exactly, yes, exactly. It is aspect ratio. So you can see these sensors, lenses. Those lenses, for example, this one, let's say this one, they are also very expensive. 24 to 70 millimeters, 24 to 70 millimeter lens. Let's say that in this question we are saying that 30 millimeters is focal length now. Focal length 30 millimeters. An object of a plane object of size 500 millimeter by, let's say, 300 millimeter is kept 1 meter away from the camera center, perpendicular to the optical axis. What is the size of the image, this object, in pixels? That's the question we are asking. Okay. So let's say if I draw this, the situation is like this now. There is the camera. Optical axis is like this. And we have a table or something. On that table, this object is placed, and for the time being, we can consider that object's size is, let's say 500 millimeter. That length we consider. $500 millimeters, and this distance we have been given as 1 meter in 1 meter, right? So if we draw the imaging geometry here, let's say that this object is 250 millimeters now. You don't have to draw it like this, okay? It works even without that. 250 millimeters, and then camera center is here, and let's say I cannot draw a ray, okay? I cannot draw a straight line. Try again. Straight line going to the camera center and striking on the image sensor. This is the image sensor. We want this distance. Yeah. How can I find that distance? We know that the focal length is 30. A center from the camera, this is 30. From the camera center to the object, it is 1000. 1 meter is equal to 1000 millimeters. Okay, 1000 millimeters. This is x. Let's call this x in millimeters. X is equal to, you can say, from similar triangles, 250 divided by 1000 multiplied by 30. That's in millimeters. This one divided by this one multiplied by 30 to get the millimeters. Now x in pixels. To get x in pixels, I have to get this quantity 250 divided by 1000 times 30. Now I have to see how many pixels per millimeter, right? So you can use this number and this number together, or you can use this one is 4,000. This is the 4,000. Okay, 6,000 corresponds to 35.9. Or this 4,000 corresponds to 23.9 millimeters. So now this one is in millimeters, so therefore I can divide this by 35.9 and multiply by 6,000. That will be in pixels. How many pixels? So let me do the calculation. 250 divided by 1000 times 30 times 6,000 divided by 35.9. I get 1253 pixels. 0.5 pixels. Actually, that is only this object, that is only half of that, no? X half of that. So that you have to multiply by 2, then we'll get 2506 pixels. 0.9 pixels. Okay, let me say call it 7. And on the other side, you can find that by multiplying by we can see that object size has been given by 500 by 300. So you can divide this by 500, multiply by 300, 1504. 1504 pixels. That's the size of the object. This side is this one, and of course, this will be another side like that. This side of the object is that. So you can see, if you know about the camera sensor and the distance, and you know that it's perpendicularly kept to the plane, then you can obtain the size of the object in pixels. If the size of the object is pixels is known, we can obtain the actual size if you know the focal length and the distance. The information we need to know. And also you can see that this only works only if your camera axis is perpendicular to the plane. But you can see that if it is not perpendicular, then you have to do additional things to compute the size. Yeah. Okay, I hope that is clear to you. Any questions about this? Yeah. Okay. So now we will go back to the slides again. So now what I did was I used the Sony website to know the size of this sensor. You can see it is difficult to find this information. They don't exactly say what sensor that they are using. So we want to, if we have the camera, not like a DSLR camera, we have an industrial camera, then we have to, there is a method to obtain these parameters like the number of the resolution, the principal point coordinate, all this, that the camera matrix can be obtained by a process called camera calibration. So now we are going to look at one method of camera calibration, and then there are many methods of camera calibration, and then we look at look at the software that you can use there. So camera calibration. So you can see the equation is lambda x is equal to k RTX. I hope now this is very clear to you, familiar to you. And so if you take this matrix, this so-called this is the camera matrix or the P matrix, it's a 3 by 4 matrix. 3 by 4 matrix. Okay, so given endpoints with known 3D coordinates. So for example, if you're using an object like that, these objects are specially made to do camera calibration with known 3D coordinates xi and known image points. So that means we can take an image and then the x's also we find, and these 3D coordinates we know. Then we can estimate the camera parameters. So here these people have done an experiment. These people have kept these kind of things here. They have measured the exact coordinates of those. So you can see the known 2D coordinates of the image they know, and the known coordinates in 3D also they know. They have exactly measured them. 312 points. So there are these X, these Y, capital Y and capital Z, these small X and small y on the image. So they have obtained that many points. If you know this, then you can obtain the parameters of the camera by using a process. So this is called a direct method, but now you have to locate these 3D markers and exactly find their locations to do this. It is a difficult process, right? There are many ways of doing that otherwise. I will not go through the details of that, but I will only show you that camera calibration. There's a software called camera calibration software. I will not go through the details of that. Camera calibration toolbox. This is available in Python and is available in MATLAB. So this is the camera calibration toolbox. There are many calibration examples. We will look at one of them. There you can see, first of all, you download the checkerboard pattern, this kind of a pattern, and that pattern you paste on a glass. Why do you paste it on glass? So that you know it is exactly flat like that at that time when you place it on glass. Then you can start the camera calibration process. You take 25 images or so like that, 1, 2, 3, 4, 5. They have taken 20 images. You can make more images. You can see these images have been taken of that camera. By keeping the camera in the different angles and so on, then after that, you have to click the four extreme corners of this checkerboard. So this, you have to click them. And when you click them, it will draw a rectangle like that, and it will locate the corners. It will locate the corners very well. And then there are adjustments that you can do also after corner extraction. We looked at how to extract corners, okay? I hope you remember that using Harris corners. So after the extracting corners, there are some adjustment steps that you do. So you can see the corners are not exactly there. Adjustment steps are there, and after adjusting, they are very correctly located now. Then these are all automatic. You just have to click buttons to do this. There you don't have to write code, and then it will go through this so-called camera calibration process, and then it will so have the reprojection error. What reprojection error means is you estimate the 3D locations and project them back onto the image. So error is very small. You minimize that reprojection error, and then you can, if the camera is located here, you can see the image planes. Now they have been able to estimate that the 3D pose of the image planes of the 20 images. You can see they have turned the camera in different ways, right? Otherwise, if you keep the checkerboard pattern stationary, this is where they have located the cameras in taking those 20 images. After when you run through that, you get the camera calibration matrix. You can see the focal length, FC 657.3, 657.7, plus or minus whatever. So you can see this is the focal length in pixels, and then you can have the principal point coordinates 302, okay, 303 times 242. So this is a very small sensor. It's a 600 times 480 sensor, 600 times 480 sensor, right? Yeah, something like that. And then there are other skew parameter, distortion parameter, all these parameters are there. So we will not discuss about it, but if you want to do a serious measurement using a camera, you have to know about those. Also, there are other adjustment steps that you do, and then this cone, all these adjustment steps are there because this is a very excellent software. Okay, then finally you get the camera parameters. I hope now it's sort of clear what cameras are, the action of a camera, what is a camera matrix, and when you know the camera matrix, that you can obtain the image by writing some Python code. And then we looked at the actual actual sensor in a Sony camera. Then we did a very small problem to find out when you are given the object size, what is the size of the image in pixels. And then we looked at how to do the camera calibration. So these are important things if you want to make a measurement using a camera by fixing the camera. But this is not sufficient because if the object is at an oblique angle, you cannot do that measurement. Any questions about this?
So that if the camera is out of focus, does that mean the image will not appear exactly on the sensor correctly?
Exactly. This is the case. Did I not do that section?
You can answer it later, so if you want to.
No. I should have done that part. Did I not cover this section on cameras? No, right?
No,
Okay.
I don't. So, no,
I think
sir.
I skipped it. Yeah, thank you very much. That answers the question that you have. So, okay, so let's look at the camera. This is a small lesson. We will go through that quickly. So, cameras with lenses, depth of field, field of view, lens aberration, digital sensors. We'll briefly look at that. So, these are very old cameras. And this person called Paul Debevec, he's a famous scientist. what he did was he removed the camera lenses, and then he put a little cardboard here and made a little prick here. Yeah. And then he was able to get an image like that using an actual camera. So this is the little toothpaste box exercise that we have done when you were small, right? So we had a toothpaste box like that, and we made a hole there, and we had another little box going there, and we put a tissue paper over here, right? And tissue paper, and then you are able to see an upside down image of the actual object, right? When you look from here. Yes. So when you change this, when you move this back and forth, the size of that changes. So this is called the pinhole camera model. So now the one problem is like when you have this hole, when the hole is large, there is a blur. We'll look at why that is, and so therefore we want to make the hole smaller and smaller. So you can see the hole is large here. There's a blur. What's the reason for the blur? Now let's take the tree like that, and that's a tree, and this is the hole 1D, and this is the, let's say, the film. So now you can see the rays travel. Now if you take this is the image plane. Take this point. This is the image sensor. One point here. Where from the scene can the rays come here? Okay, to this, definitely from here a ray can come because there's a hole. A ray can come from here also, just touching the edge of the hole. A ray can come from here also, just touching the edge of the hole. So therefore, you can see all these points in the scene give light to this point. So therefore, there is no one-to-one correspondence between the scene and the image. Because of that reason, your image is blurred. So now you can clearly see, I want to cut off these rays that come and strike the camera film. I want to cut off those rays. When you cut off those rays, that means you are making the hole smaller. So you can make the hole smaller, then the blur reduces. The hole is 0.mm, 0.6, hole much smaller, 0.35, it's quite sharp. But now you want to make it even sharper, you use. So still reduce it. When you still reduce it, you will get the so-called diffraction effects. This is not refraction, this is diffraction. Diffraction means at a sharp edge, the light bends. At a sharp edge, light bends, right? Like that. So this is called diffraction effects take place. So therefore, the pinhole camera is not a good thing. When you have a pinhole camera, not enough light comes to the sensor. So therefore, you have to have a very bright scene to make a point, make an image. So to handle those reasons, that means to obtain proper focus and to have enough light coming and impinging on the sensor, you have a camera lens. So that's why you add the lens. Now you can see with the lens, you can have one-to-one correspondence. You know that with the lens, the rays that go through the lens center do not bend, but parallel ones, they go and strike the point at the focal length, right? You know these things. So therefore now it is this point here corresponds to one point on the film on the focal plane. Yeah, a lens focuses light onto the film. So this is called thin lens model. Rays pass through the center are not deviated. This is called the pinhole projection model still holds. So this is called the focal length, as we know. So parallel rays go and strike there, focal length. The lens focuses light onto the film. Yeah. So the situation. Now, if you take, okay, the thing is, for this plane, this particular plane, this plane is in focus. That means one-to-one correspondence for that plane. But if you take another plane, if you take another plane here, is another plane here, that is not in focus. So you can see there is no one-to-one correspondence. So this thing is called circle of confusion. One point here corresponds to a circle here. So that's the reason for the blur, circle of confusion. So, and also thin lens formula, there are so many similar triangles here. So similar triangles everywhere. So you can, if you consider these two triangles, y prime is the height on the image, y is the actual height, y prime divided by y is equal to d divided by d prime. Yeah. Then there's a similar triangle here also. Y prime divided by y is equal to d minus f. Yeah, d minus f. These two triangles. This is the this will give you this formula 1 over d prime, 1 over d, 1 over f. 1 over d prime is the image plane to the lens, and this is the lens to the object. So as you know, this is called the thin lens formula, which we did in the O levels. So there's something called depth of field. Certain range is in focus, others are not in focus. So in this image also you can see the things that are close by are in focus, not in focus, blurred. These are blurred. This region is in focus. Yeah, let's see why that happens. So now that happens because of the so-called aperture of the camera. That means you can open the opening or the aperture through which the light comes to the camera. So you can see this is a large aperture. Opening is large. This one is a small aperture. Opening is small. So let's take 3 points. This point number 1, point number 2, and point number 3. When this is largely open, light going from point 2 strike the film here. That's fine. Remember, now the aperture is large. This is the aperture, full aperture. Light from point 1 goes and it focuses here. So therefore, the circle of confusion is there here. Here is the image of 1. If you take 3, light focuses somewhere here, and there's a circle of confusion here, like that. So only the light coming from plane 2 is in focus. All others are defocused because the aperture is large. So you can see the back. This is maybe you can this background very close to the camera are defocused, but a certain plane is in focus. This is the reason for the depth of focus. But if you have a very thin, very small aperture like so, both 1, 2, and 3 are sort of in focus because the aperture is small. You can see this is the aperture. They are showing the aperture here. So these are the parameters that you can control in the camera. You can control the aperture camera or the f number. You can control. The size is inversely proportional to the f. Range aperture size affects the depth of field. A small aperture increases the range in which the object is approximately in focus, but a small aperture reduces the amount of light that. So therefore, we need to increase the so-called exposure, the sensitivity of the CMOS sensor. We have to increase. So you can see here also the depth of focus effect. Large aperture, small depth of focus. These charts are not in focus. Small aperture, large depth of field, everything is in focus. Yeah. Then the field of view of a camera is there. So that is this angular thing. What determines that? So you can see this is the size of the CCD, and the parameters of the lens can focus light from here. So this is this angle P is equal to tan inverse D divided by 2F. Yeah. Focal length and the size of the length of the sensor control that. Larger focal length, smaller FOV. So this is what we are showing here. So you can see this focal length is 17 millimeters. The whole scene is in display. 28 millimeters, slightly focal length is increased. The amount of scene that you see here is like sort of this part, right? And then more focus, then you can see the two people are visible, and focal length increases, like that, and you further increase, and then you can see the people on the deck when you have focal length like 1000 or so. So there are things that people do with tricks now. They can get the same object size. Now you can see the car is of the same size in the image. What they did was when the person moved far away from the car, he increased the focal length. So took a 24 millimeter focal length image here and 125 millimeter focal length here. The car is of the approximately the same size. But you can see in this one, the 3D nature is there. In this one, 3D nature is gone. That's what happens when you use a telephoto lens. That means with a large focal length. Small FOV, small f, a camera close to the car. small FOV, large F, camera is far from the car. So when you are making portrait images, you can see that this is the better looking one. Here the camera is too close to the person. Here the camera is too far from the person. So face looks flat here. Face looks too 3D here. Face looks flat here. If you take an image like this, you will be scolded by the subject. This also. This one she will like. Yeah. Okay. You can see that, right? And then approximating an orthographic camera is possible with so you have the extreme, the perspective camera. If you use a perspective camera, you can see the actual parallel lines on the scene are not parallel anymore. But if you use a with perspective camera, you can see the lines are sort of parallel. So we can do that with a telephoto lens. And these kind of different dolly zoom and so on are there. You can read about that by using the slide and so on. Funny things there. So then problems with the lenses are there. I have heard that these lenses are made, they take the glass and mold the silica and then slowly cool it to get these lenses. Lenses are very expensive, as you know. So you can see one effect is called vignetting. The light that are coming from going at the very edge of the lens, they escape. So you can see at the four corners, you will have darkness. So you can simulate an old picture with adding the vignetting effect, because all cameras had this problem. Now I think they have somehow corrected it, I don't know. So then radial distortion is there. So this one has no distortion. If you take a rectangular grid, the lines are straight. But here you can see in this image, they are like the curves. This is called the barrel distortion and the pincushion distortion. These distortions can be corrected if you calibrate the camera and obtain the so-called K parameters. I think you saw them when I showed you the camera calibration results. And the spherical aberration is there. Spherical lenses don't focus light perfectly. Rays from the optical axis further away from the optical axis, focus closer. That kind of thing is there. So you can see this as focus closer, these two. So that has to be corrected. And chromatic aberration is there. Lenses has different refractive indices for different wavelengths. So red bends and green bends and blue bends too much. So it focuses here, green focuses there, red focuses there. So at the edges, you can see this haloing effect. The digital sensors, we talked about digital sensors. They were CCD, now most of them are CMOS. And Bayer pattern, we talked about the Bayer pattern before. To remind you again, so the lenses, the sensors are of one single array of pixels. Color sensation you get by having a filter on top of the sensors. So like that. So this filter is blue filter, only blue light passes through that. Green filter, green light, red filter, red light. So you can see every pixel does not have every color. So green is more because human eye is more sensitive to green. So these colors we have to interpolate and get all three colors. Why more green? Because human eye is sensitive to this range of light. Okay. So you can see the color more, these problems are there. So that comes because of the interpolation that you have to do in a digital sensor. I will not talk about it too much. You can study that. So miscellaneous digital camera artifacts, noise is there. Low light is where you most notice noise. High sensitivity ISO number is required to correct that. But now new sensors have very powerful, very high ISO number. You can go to that. So then stuck pixel problems are there. In-camera processing sometimes give halos like that, but now I think those are mostly gone. Compression, JPG artifacts are there. You can see color. JPG artifacts are ringing effects actually. Just I mean these are colors due to the blooming. Color artifacts, color more purple regions. I don't know too much about this. So, but if you want to study about cameras, I think if you please study, and photographers know these things. I think. So some history about these cameras also. Kodak produced the first digital camera, but they went into extinction, that company. First digital scan photograph. So these are how the cameras have risen until 2015. Now billions of cameras are there because of the mobile phones. Yeah, that's the camera lesson. I hope that now that the problem is clear.
Thank you, sir.
Yeah. So I forgot to do that lesson. Okay, so let's take a break and then we will start the CNN lesson, convolutional neural networks, and uh, we will do parallelly like this because we have to cover a couple of things, more about 3D reconstruction also. So let's meet at about 8 17 or so. I pause the recording. So the convolutional neural networks are now a very popular technique of classification of images, object detection, and so on. So we will study this and gain experience in using uh, PyTorch to code one of these networks, to code very simple ones and make use of existing pre-trained convolutional neural networks. But that we need to understand a few things. Mm. First of all, we will briefly see what a linear classifier is. Uh, Now assume that you have input images. Maybe we want to classify these input images between cats, dogs, and sheep. Only three classes. Now assume that this cat image can be represented using four numbers: 56, 231, 24, and 2, which is not so. Maybe you need many more numbers, but for this story example, let's consider with four numbers you can represent that. Now, these are weights. This row represents the weights for the cat class. Now what you do is with this number you multiply 56, with this number you multiply 231, with this number you multiply 24, and with this number you multiply 22. And then you add this so-called bias term, and then you get the cat score. Similarly, you will get the dog score, and similarly you will get the sheep score. Right now, as it stands, you will call it a dog. Why? The dog score is the highest. Why is it predicting the cat incorrectly as a dog? Because we have not adjusted these W's. We have not changed these weights and the biases. So how do you change them? Now, when it is given an input image, a cat, and it predicts dog, that's an error. So we capture that error, and using that error signal, we change the weight through a process called, in neural networks terms, backpropagation. In here, we can use a simple optimization scheme. So once you do that, and if you take this row, remember it is just not four numbers, it will have many more numbers. For this story example, we are showing four numbers, and arrange those many numbers into the shape of an image, and you will see for the car row, you will see a car, blurred car. That's like a template. For the horse one, you will see an image with horses pointing leftward and rightward. Why? In the training images, the horses were like that. So this is the thing called a linear classifier. Why? Because we are multiplying, taking W and multiplying X with W and adding a bias. So you can see it is like Y equals, yeah, MX plus C, right? It's a straight line. MX plus C, something like that. But in multiple dimensions, you can see multiple numbers must be there. 1, 2, 3, 4 numbers in W now, in this case, and one bias term. So this is a linear classifier, a line, then a plane in a hyperplane, and so on. Okay, so the so-called perceptron that was discovered in 1958 by Dr. Rosenblatt does exactly the same thing. Now you have x1, x2, x3, up to until xd. Remember in the previous example, d was just four numbers. And then you have the w's, w1, w2, w3, up until wd. And you take w and multiply that with x, and you add a b. And then if you get the sign of that, if the sign is positive, you can call it a cat. If it is negative, you can call it a dog. So this is called a binary classifier, but it is a linear classifier because you can see it is wx plus b, it's just a straight line. If you capture b also into w, we can write sin wx X is d-dimensional, W is K times d-dimensional. Assuming K classes, it's not a powerful classifier. Now, before this neural network paradigm came, people used bag of visual words, and there what people did was they extracted local features. For example, you can see that this is the Mona Lisa image. From that, they picked image patches like this, and then they had so-called a dictionary of patches. You can see these 4 patches are in the dictionary, and they uh, check in every image how many of those patches are present. For example, for the Mona Lisa image, this skin color patch is many, and this eye patch, they will have many, and so on, right? But for the bicycle image, the bicycle seat will have many. For the violin, this thing will be many. So you can see by getting a histogram against the code book, we call it a code book, you can sort of classify to which class this image belongs. So first of all, we had learned the so-called visual vocabulary. Visual vocabulary is this one, and then quantize the local features into the visual vocabulary. We have to see that, okay, this image is this one, like that we have to quantize them into the visual vocabulary and represent images by the frequencies of the visual vocabulary. These are the frequencies, as you can see, these are the frequencies, and then train a classifier like support vector machines. Okay, that was the bag of visual words paradigm that came before. And then this was developed into slightly complicated one by dividing the image into many rectangles and getting so those histograms in those rectangles also into a spatial pyramid. But those were all things. But with neural networks, because these neural networks are identified as linear classifiers, they introduce hidden layers. Okay, but each of these nodes will have to have a non-linearity. You can see this is the sigmoid function. This shape is like this. When t is, okay, this is t. When t is minus infinity, you can see this is e to the power of large number. That means it's 0, so 1 divided by 0, it's 1. So I'm sorry, e to the power of minus infinity, this e to the power of large number, it's a very large number, it's 0. When e is positive infinity, e to the power of minus infinity, so that means 0, 1 divided by 1, 1. So you can see that function is like that, right? That function is like that. At when t is equal to 0, e to the power of 0 is 1, so this is 0.5. 1 divided by 2 is 0.5. That's a sigmoid function. You can see it's a nonlinear. It's not nonlinear function. It's not a line. So that's why it's called a nonlinearity. So if we add one more layer, okay, one more layer like that. So you can see you can have W2 plus W2 and W1. Excuse me. But those also we can combine into one W. Just the matrix multiplication, right? Where W3 is W2 plus W1. So still a linear classifier. So to have a powerful classifier, nonlinearity is extremely important. So if we add nonlinearities, we can learn a continuous boundary. So here max function is a nonlinearity. So I will show you what this looks like. For example, take W1x, not for example, W1x, and let's draw this. So here is a graph I'm drawing. So this axis W1x is there. W1x, the value that you get from W1x. Now what we want is maximum value among 0 and W1x. Maximum value among 0 and W1x. There are two numbers. Assume that your W1x is negative. If your W1x is negative, that means we are considering a value like minus 5. Let's assume that W1x is minus 5. Now you have 0 here, and this one is minus 5. What is the maximum value between 0 and minus 5? Of course, 0. So you can get 0 there. You can see for any negative value of W1x, what you get will be 0. So in the negative side, the graph will be like that, 0. Now think about a positive value of W1x. Let's say, for example, 3. So you have 0 and 3. What is the maximum value between 0 and 3? 3. You can see it will be like that. For 2, it will be like this. For 1, it will be like this. So you can see now the graph is like that. Yeah. So this is, you can see at the center, there is an, at 0, there is a nonlinearity here. So this is a nonlinear function. This is the so-called famous ReLU nonlinearity, rectified linear unit nonlinearity. So you can see when you add a nonlinearity, now the neural network first layer is bank of templates. Second layer recombines templates, something like that happens. So this is one of the most important interventions in the neural network domain, having this ReLU nonlinearity. So there are other nonlinearities also. ReLU is what we will be looking at. So PyTorch has all these ones: sigmoid, hyperbolic tangent, leaky ReLU, and so on. Nonlinearities are there. So people constructed multiple layers. So this kind of thing is called MLP, or a multi-layer perceptron. So even if you take the recent advancements, 2017 is the year in which this Vaswani's attention is all you need paper was published. We call it the transformer paper. There, within the transformer, there's a multi-layer perceptron. So you can see multi-layer perceptron is still very important. Think about the multi-layer perceptron is, you can see that this, if you take a node here, that is connected with all the nodes in the previous layer, all of them. So let's take, for example, you take a 100 by 100 image, 100 by 100. There, that means 100 by 100 pixels are there. That means there are 10,000. 100 by 100 is 10,000 nodes. 10,000 nodes. As in here, you have, let's say, 120 nodes. 120 nodes. How many weights are there? You can see for each of the 120, there are 10,000 connections to be done. So therefore, you have 10,000 times 120 weights, connections. Yeah, and of course, you have, for each of these nodes, you'll have bias, so therefore 120. This is the total number of weights in that layer. In this layer, many more weights. In this layer, many more weights. In this layer, many more weights. So this is what these weights are, the ones that remember uh, the information about the task that the network has to do. Yes. Now, how do you now finding these weights is the thing. So when you find these weights, you would have optimized the network. How do you optimize this network? Or how do you find these weights? We find these weights by this process called gradient descent. So what is gradient descent? In gradient descent, think about this now. Uh, in the gradient descent, if you are on a mountain top or something here, mountain top here, this is a mountain, okay, and you are here. You are here. If you want to climb down the mountain the fastest, in which direction should you move? You should move. You should not move like that, okay? If you move like that, you'll be going in circles. You should move along the steepest direction, steepest slope, steepest slope. That's when you can go to the bottom as fast as possible. So this is called descending along the gradient. Actually, the negative direction of the gradient. So let's take another simple function. You know about this function. This is some function like this, okay? Is actually a parabola, right? The parabola. So maybe you can see that this is like x minus 3 squared or something. You don't have to worry about that equation, especially x minus 3 squared. Now, this is the minimum. What we want to go is to the minimum. So we are standing somewhere. We are standing somewhere. Let's say we are standing here. This is where we are. That's the x location of x, where I am standing. And then, okay, in which direction should I move? I have only two choices, okay? I can either move this way or I can move that way, because this is like a rope. I'm standing on a rope kind of thing. It is not a two-dimensional mount or something. One-dimensional function. I'm standing in a rope. I can go this way or that way, left or right. In which direction should I go? So that we can decide by looking at the gradient of this function. Gradient is a slope. So I'm drawing the tangent to the function here. Sparshaka tangent. That's a tangent to the function right here. And that makes a small angle with x-axis. Therefore, my gradient is positive. I hope you agree with that. Gradient is positive. So we have to move in the opposite direction of the gradient if you want to go to the minimum. So gradient is positive, that means right toward the right side. So this is positive. So that means x positive is this one. So we have to move in the opposite direction of the gradient. So you move like that. You move in the opposite direction of the gradient. How much? That we can think about later. So assume that by this motion, you came to this point. Now you are standing there. You are here. Now you estimate the gradient again. Now the gradient is like this. Is the gradient positive or negative? Gradient is still positive. Because it is positive, you move in the negative direction of the gradient some step. And hopefully by doing this, you will slowly come to after several steps, come to this minimum. Hopefully. Not all the time, hopefully. Actually, I need to be very careful here. This arrow is too long. I will go small arrow. After several steps, you will reach there. Many more steps will be required to reach there. And the arrows usually become smaller and smaller when you. Okay, now take the condition where you are right here. That's where you are now. Now you estimate the gradient again here. Gradient makes a large angle with respect to the x-axis, so therefore the gradient is negative. So negative direction, that means the gradient is pointing this way, but you have to walk in the opposite direction of the gradient. So you move this way. So you can see by step going, hopefully you will reach the minimum. So this is called gradient descent. But I showed you only in 1D gradient descent. But if you go in 3D, 2D, you can see maybe you start here, go like that, like that, like that, like that, and reach the minimum. But of course, you can see in this landscape, there are many minima. Then there is a chance that you will, if you slightly change the starting position, you will reach a different minimum. That happens. So this is a 2D's case, only 2 W's. Here there's only 1 W. I wrote it X actually. I should have written it as W. So, but in the neural network, this is extremely high dimensional. So, but moving along the negative direction of the gradient is correct. This moving along the negative direction of the gradient. This alpha says, like, how much should I move? So this is called the learning rate. Learning rate, how much should I move? So I have written here the landscape of this function's equation, yi correct label minus what the network predicts squared. So it's a square of this. So therefore, it is in this case, it's a so-called convex function. You can find the minimum in this case. And there are some regularization term also. This is called the loss. So this gradient descent, through gradient descent, you can go to the minimum. When you go to the minimum, you would have optimized the W's. So you can see W optimization equation is this one, the gradient descent equation. Any questions about the gradient descent to find the parameters of a neural network? But we don't use manually. We don't manually code. We will use the existing framework for that. We will use TensorFlow.
So I have a question. It might be foolish, but I'll ask it. That summation, why is I starting from 1 instead of 0?
Yeah, that's a good question, but I think it's a convention, right? They decided to start from 1. So they called, okay, these are for different training examples. Not only one training example, many training examples, many cat images are there, right? Maybe 100 cat images, 100 dog images, so on. So they decided to call the first cat image I equals 1.
Oh, instead of 0. Okay, got it, sir.
Yeah. Because this is not like sort of mathematics, first image or something like that. So this n will be okay if you have 5,000 images each and you have 10 classes, you will have n will be 50,000. 50,000. But that brings us to an important point. You usually do not construct this function with all 50,000 examples. You take 500 at a time and so on. So that is called a batch. So because you took 500 images and constructed this error function, when you take the next set of images, it will be a slightly different error function. That's why we call it stochastic gradient descent, not gradient descent, because this error function changes from one batch to the other. Stochastic. There's a statistical thing. Okay, update weights by gradient descent. But what is backpropagation? Now, in this neural network, there are so many weights, and the L's dependency with W will be through many layers. So therefore, computing partial derivative of L with respect to W is not possible directly. You have to go through the so-called chain rule. I hope you remember the chain rule. I will show that later. Chain rule. So backpropagation is through the chain rule. You can compute the partial derivatives by backpropagating the gradients. Propagating the gradients backward. This is why it is called backpropagation. This is the most important technique used in training of neural networks. Stochastic gradient descent, I told you what it is. Compute the weight with respect to a small batch of examples, then we get the stochasticity. So you cycle through the training examples in random order in multiple epochs. When you cycle through all the 50,000, you call it an epoch. Okay. Yeah, so that was briefly about the neural networks. Then in 2012, as I have told you, a great advancement happened. So there was this thing called ImageNet Large Scale Visual Recognition Challenge, ImageNet Large Scale Visual Recognition Challenge, and people were making about 26% or something errors. But with this advancement that happened in 2012, the error was reduced so much. Now, this kind of thing does not happen in computer vision. So everyone's attention was on this so-called AlexNet. It was an 8-layer network. So I will show you the pictures of the AlexNet authors. I think I have shown this before. These are the authors of the AlexNet. You can see this is Ilya Sutskever. This is Alex Krzyzewski, and this is Professor Jeffrey Hinton. These great people. So as you know, in 2019 or so, Turing Prize was won by these three people, Joshua Bengio, Jeffrey Hinton, and Jan LeCun. And in 2004, I think, as you know, Professor Jeffrey Hinton won the Nobel Prize. And won the Nobel Prize, Nobel lecture by Professor Hinton. When you go for the Nobel Prize, you wear so-called white tie, right? Highest honor. This is the great advancement that happened. Okay, what happened to Ilya Sutskever? Alex Krzyzewski, I don't know, I didn't search, but Ilya, as you know, he was the chief scientist at OpenAI. So OpenAI's all these great works of OpenAI, ChatGPT, and so on is mainly due to I think Ilya. So amazing, right? So this we have done. So what India has done. You go to Scholar and search for India. You can see this AlexNet paper has 192,000 citations. This is more than the DNA papers citations the DNA paper has. So amazing contributions by these people. So continuously publishes things, and GPT, about GPT, uh, many publications of GPT papers. Yeah, you can see that. So this is that the thing. So it was an 8-layer network. So we look at that network also. So that was a convolutional neural network. So for that, we need to understand what convolutions mean. Okay. So now, if you watch this, you will be able to understand what those are. But we have done that in regard to the spatial filtering, right? We took this 109, this averaging kernel, right? All numbers are 109 here because you are dividing by 109, and you keep that kernel on the image like so and multiply the underlying number, so all zeros, so you get 0 here. Now this 90 is there, 90 divided by 9 is 10, you get 10 there. I think you know what these convolutions are, right? We have done the convolutions. Yeah, so from fully connected to convolutional network, so this is a fully connected network, densely connected network, or we call it an MLP, multi-layer perceptron. Okay, now in the fully connected network, to compute a cell in this layer, for example, cell here, you get input from all others in the previous layer. All others in the previous layer. That means all the nodes in the previous layer are connected to this one. If you take another one here, all of them are connected, right? Yeah. So, but in convolution neural networks, it's not like that. So let's take an image of 32 by 32, and it is a color image. Depth is 3. So we call the depth as the number of channels the image has. So it has the color image 3. So you place a convolution kernel here. So you can see that this convolution kernel, we consider that to be a 5 by 5 kernel. Remember, although we call it a 5 by 5 kernel, always the depth is there, depth is 3. We don't even talk about the depth. Fully spans the depth. Okay, so now to compute the number value at one element in the next layer, in the next tensor, we will do 5 times 3 dimensional dot product multiplication. Yeah, underlying pixels you multiply by all the numbers in the kernel. So extends the full depth of the image. So once again, so 5 times 5 kernel, and that produces, and we have to add the bias also. So that's the kernel. So okay, now these are learned. These numbers in the kernels are learned. So one kernel gives one feature map. Yeah, if you have multiple kernels, maybe 32 of them, you will get feature map, 32 feature map. We call it the feature map or the activation map. Okay. Okay, now then in the next layer, we will have a kernel 5 by 5. We call it a 5 by 5 convolution, but remember, these 32 dimensions, it fully spans the. To compute one cell, you have to do that many computations. Yeah. Okay, now let's try to study this even further. So I have shown you 32 by 32 by 3 color image. So filters, 6 filters. So let's take the first convolutional filter. I am showing here. So I am showing that on the image also. Due to that, you will get a plane here, a feature map here, and there's a bias one also here. Okay, that feature map will be 28 by 28 by 1. What's the reason for the size being reduced? Because this is a 5 by 5. You can see the kernel cannot fully overlap with the image. You lose 2 pixels from the top, 2 pixels from the bottom, and you get this feature map. And another layer, Another convolution kernel gives another feature map. Another convolution kernel gives another feature map. Another convolution kernel gives another feature map. So like that, I am considering there are 6 such filters. Therefore, this tensor will have 6 channels, like this, because there are 6 convolutional kernels. So 20 by 8 by 20 by grid, at each point there's a 6-dimensional vector. You can consider like that. At each point here, you have a 6-dimensional vector if you want to consider like that. So stack the activations to get a 6 by 28 by 28 output image. It's not an image, we call it a tensor. I hope this is clear for you. But now this is not all. We will usually send a batch of images. Now let's consider a batch of 4 images. For the first image, you will see you get a feature map of depth 6. And for the second image, you get a feature map of depth 6, 6, and 6. So altogether, because of these 6 filters, you will have 4 times 6 times 6 times 4 times 6 times 28 times 28 tensor because of the batch. So you send the images in batches. So this is the structure that we'll get as the output. So all these things will have to be held in the GPU, graphics processing unit memory. So in slightly more general terms, assume that there are n images in the batch. Each image will be maybe can be 3. It's color image, and then h times w is the height and width of the image, and then you have that many convolution kernels. See out convolution kernels. So each filter will be k times kw. So this is maybe 5 by 5. And C in will be the depth of the kernel. So it will be number of channels in the kernel. In this case, it's 3. So you will get C out for each of the images. C out many activation maps. So finally, the tensor size will be n times C out times h prime times w prime. You know how to compute h times h prime and w prime. Yeah. So when you do this in the AlexNet, for example, when they ran these convolutional kernels, they had 2 GPUs, the top GPU and the bottom GPU. In the top GPU, these kernels, you learn these kernels, turned out to be edge-like patterns, and in the bottom GPU, they turned out to be color patches and so on. So people are very happy to notice these things. Yeah. Okay. So now let's see these convolutions as speech extractor. So you run the convolution kernels. I'm pictorially showing that kernel like that. Then when you run that throughout the image, you get a feature map. You run another kernel. When you run another kernel, you get another feature. Like that, you get many feature maps when you run a convolution, when you run multiple convolution kernels. So you have an input image, you run learn convolutional kernels, these kernel values are learned, and then we do apply a nonlinearity, we do so-called spatial pooling, and then we get the feature maps. Okay, so let's look at this nonlinearity. This is the ReLU nonlinearity as I spoke to you about before. Greater than 0, it's actually the same, you get the same value. Less than 0, you get 0. That's the ReLU nonlinearity. It's very, very important. And then spatial pooling is what? So you get a certain patch and divide, you should a 2 by 2 patch and you half the size of this. This is important because you have to reduce the feature size so that the convolutional neural network in latter layers have more and more global views. Yeah. So this key idea of AlexNet was the stacking of these layers, conpool, 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 conpool. We had 5 convolution layers and you had 3 dense or fully connected layers. Yeah, dense. Yeah, that's the AlexNet. So, okay. Any questions up to now? Please don't hesitate to ask questions.
So did they have GPUs that time in 2012?
2012, yes, they had the GPU. They had GPU.
Oh, okay.
580. They used the GTX 580. I think. I'll show you. I have a slide. So let's look at the shrinking due to the convolution kernel. So you can see if you place the kernel, place the kernel like this. Only center that you can place the kernel is here. So you cannot place it here. It's not possible. So because of that, you lose this top row, bottom row, right row, bottom row, and the left row. If you have a 3 by 3 kernel, right? We have studied this before. If you have 5 by 5 kernel, you use 2 pixels from all around. Yeah. So for example, if you have 10 by 10 image and you run the 3 by 3 filter, you get an 8 by 8 output. So how do you actually compute that? If the input size is W by W, filter size is K by K, output size will be W minus K plus 1. W minus K plus 1. So in this case, 10 minus 3 plus 1. 10 minus 3 plus 1 is that 10, is this 3. Yeah. Okay, to get the same size after convolution as the input image, we do a certain thing called padding, a padding P. So we, for a 3 by 3 kernel, we add a padding of just 1 pixel. For a 5 by 5 kernel, we add a padding of 2 pixels. For a 7 by 7 kernel, we add a padding of 3 pixels. That padding size we can compute as K minus 1 divided by 2. So this is the output size now with the padding. Okay, there's a thing called receptive field that is like this. Now, if you take a layer, a tensor here, now we have one cell there in that tensor. That corresponds to 3 by 3 in the previous one, right? If you take this extreme, this cell, that corresponds to 3 by 3 here. If you take this cell, it corresponds to 3 by 3 here. So now you can see this is totally a 5 by 5 window. So you can see this one single cell's values were from a 5 by 5 window 2 layers ago. If you go to even one layer before, it will be a 7 by 7. So you can see the so-called receptive field increases as you go down the layers. So each successive convolution adds k minus 1 to the receptive field with L layers. The receptive field size will be 1 plus L k times k minus 1. That's how you compute the receptive field. That's why the convolutional neural networks will have a large depth, so that you have a large receptive field. That means information from a large size of the input image, large range of the input image is captured in one cell in the output layers. Receptive field grows linearly with layers. It's a downsampling scheme. So then there's a thing called stride. How much do we move this kernel at a time? How much? So you can see in this case, the stride is 2. You have moved the kernel center by 2 pixels, not just by 1 pixel. So because of the stride, you can see directly the image size reduces. That reduction is by this, you have divided by the stride 2. So if you are moving by 2 pixels, you have divided by the 2. So output size will be W minus K plus 2P divided by S plus 1 now. So we are going step by step to understand how these convolutions and tensor sizes can be computed. Okay, and there's a thing called 1 by 1 convolution also. This is, for example, a 5 by 5 convolution. So 1 by 1 convolution means you do it like that. This is 1 by 1. But remember, the convolution kernel fully captures the depth. Depth is 32, for example, and so on. So now let's do a small exercise to compute the number of learnable parameters. If an input image is of size 30 by 32 grayscale, and there are 6 filters of dimension 5 by 5, and if stride is 1, padding is 2, compute output feature map size, number of learnable parameters, 3 number of learnable parameters in the image were a color image, 4 number of multiply and AND operations. I'll give you a second to think about it. Okay, so let me solve this slowly. It's a 32 by 32 grayscale image, and there are 6 filters. Dimension of it is 5 by 5. Stride is 1, padding is 2. compute the output feature map size. Input image is a 32 by 32 by 1 image because it's a grayscale image. So this one is 1. This is 32 by 32. The padding is 2. Stride is 1. So therefore, if you use this equation, W minus K plus 2P divided by S. Plus 1. So therefore, W is equal to 5. I'm sorry, image W is equal to 32. K is equal to 5. Padding is equal to 2 times 1. Divided by stride is 1 plus 1. How much do you get here? 32 minus 34. 34 minus 5 is 29 plus 1 is 28, right? 28 by 28 is what you get. Compute the output feature map size. Number of learnable parameters. To compute the number of learnable parameters, we have to consider how many convolution kernels are there. So these are 1 times 5 by 5 kernels. You have 6 of them. Plus there will be bias of, for each of them there will be bias 6. So 25 times 6 is 150, 156. 156 is the answer for that. Number of learnable parameters is the image or a color image. If the image or a color image, instead of this 1, you get 3, right? 3 times 5 times 5 times 6 plus 6. 456. Yeah, yeah, okay. Oh, I think I made a mistake here. Adding is 2. Oh, this is 2p. I made a mistake here. Yeah, I'm sorry, I made a mistake here. I put stride is 1, padding is 2. I had to put 2 here. So 32 plus 4 is 39 minus 5 is 38. So this is wrong. 32 by 32. I'm sorry about that. Number of multiply and add operations. To do that, we have to consider the size of the output feature map for the output tensor. The output tensor is, as you can see from here, it's a 32 by 32 tensor. And the depth is 6 because there are 6 convolution kernels. So to compute each of these cells in this, you have to give computational power because you have to run a convolution for the color image. So each of the convolutions will cost you 3 times 5 times 5 multiplications. So you have to get t times 5 multiplication, and then you have to multiply that with 6 times 32 by 32. That's the total number of computations that you have to do. Multiply operations. Here are the answers. Yeah. Yeah. So yes, the output feature map size is this one, and for each of them 3 times 5 by 5, right? Okay. So that's this is a summary of what we discussed, convolution summary. Input size is C in times H times W, and parameters K times KW kernel size, output that many filters, stride is P, padding is P, stride is S, then H prime is this one, W prime is this one. So you have to remember that. So the common settings are like this. K equals 3, P equals 1, S equals, this is the most common settings. Yeah, so let's look at the other operations later, and then we'll do some coding also next time. But please go through a Python tutorial. I'll find a tutorial and send you over the WhatsApp. Please go through that so that you can be ready next time when we code. Okay, so if you have any question, you can ask. Otherwise, we are done for tonight. Thank you so very much for staying for 3 hours, and I wish you a pleasant rest of the weekend. If you have no questions, you can log off. Thank you very much.
Thank you, sir.
Thank you.